Hello, I'm Toryn. This paper, Changing Beliefs about Domain Dynamics in the Situation Calculus, is joint work with Sheila McIlraith and Hector Levesque. In this work, we're concerned with modeling an agent that can change its beliefs about domain dynamics, that is, about action effects, preconditions, and sensing, as a consequence of its observations of the world. We propose a way to conveniently represent domain dynamics in the situation calculus to support such belief change, and we focus on how the specification can control how general conclusions an agent draws from observations. To illustrate, let's consider an example with this robot. The robot initially believes that if it tries to pick up anything, it will be holding it. So that's a belief about the effects of an action. Now, suppose that the robot fails to pick up the cup. Note that this is not consistent with its belief about the effects of actions. So, when the robot observes that it has failed, it should change its beliefs about the action's effect. One option, shown here, is that the robot believes that if it picks up anything, it will be holding it, with the exception of that one cup that one time. So that's a very narrow change. Now, suppose that the robot fails to pick up the cup again. On observing that, the robot again has to change its beliefs in some way. Here, the robot now believes that if it picks up anything, it will be holding it unless it's that cup. So now, the robot has drawn a more general conclusion. Finally, suppose the robot now fails to pick up a different object. This time, the robot may decide that it can only pick up non-slippery objects. So we want to be able to come up with logical theories to describe this sort of thing, so that these changes of belief will come out as logical consequences. We'll be working in the situation calculus, so I'll give some background first. The situation calculus is a second-order language. Situations represent histories of actions, organized into trees, where the edges correspond to actions. So from any situation, you can do various different actions which lead to different possible futures. Properties that can change from one situation to the next can be modeled using fluents, which are predicates that take a situation argument, that describe what's true in a situation. So, for example, you might have a fluent holding, xs, saying that object x is held in situation s. Since the situation calculus uses standard second-order logic, in order to describe how actions behave and how the situation trees are organized and so on, you need to have theories that contain appropriate axioms, and these are called action theories. I'll say more about those in a bit. Sometimes, action theory as a whole is taken to represent the knowledge of the agent, but we'll be modeling beliefs explicitly within the language. The standard way of describing belief in logic is in terms of possible worlds. So there'll be an accessibility relation to describe what worlds are epistemically accessible. This is commonly done in modal logics, but it can also be described within classical logic by encoding the accessibility relation using predicates and representing the world as some sort of objects. In particular, you can represent the worlds as situations in the situation calculus. To specify how beliefs can change and be retracted over time, further structure beyond the possible worlds model is needed. Shapiro et al. Proposed an approach in the situation calculus where belief is defined as what's true in all the most plausible, accessible situations. Sensing actions cause situations that are incompatible with the sensor's results to become inaccessible, which allows for belief revision, since the set of most plausible accessible situations can be completely replaced. In previous work, we proposed to measure plausibility by counting the number of abnormal atomic formulas true in a situation. Note that this is closely related to cardinality-based circumscription, a non-monotonic reasoning technique from the literature. So we continue to follow that approach in this work. Here is an example to illustrate how this works. In this graph, the nodes represent different situations, and these edges represent the epistemic accessibility relation. So let's say the agent is in S0 on the left. So the accessible situations are S0 itself, S1, and S2. Now we see that each situation has various propositions that are true at it. For example, in S0, the fluent ab, which is a special abnormality fluent, is true, and P is false. It can be seen that the accessible situations from S0 happen to be those situations where not ab implies P is true. And among these accessible situations, it can be seen this unique most plausible one, which is S2, because the ab predicate is false there. Fewer abnormalities is more plausible. In general, of course, there may be multiple most plausible accessible situations. And we see that each most plausible accessible situation, that is S2 in this case, P is true. And therefore, the agent in S0 believes P. So, in the action theories we're considering, there needs to be an axiom describing the initial accessibility relation. We also have the standard sorts of situation calculus axioms. There are initial state axioms describing the actual initial situation, and successor state axioms, or SSAs, specifying for each fluent how its value in a situation relates to the previous situation. Will require that each abnormality fluent, ab I, has this SSA, which says that it isn't changed by actions. So what's abnormal stays the same. That constraint is not a great limitation, as we can represent implausible events as being predetermined by the initial situation. Note that abnormalities need a situation argument, despite not changing, so that we can associate different plausibility levels with different initial situations. Finally, there are precondition axioms and sensing action axioms, which describe how the agent can gain information from actions. And there are some other axioms that I won't go into here. So now that we've covered this background, let's consider beliefs about domain dynamics. Note that a theory's axioms describing dynamics apply to all situations, and so to all accessible situations. Therefore, the theory entails that the agent always believes them. However, the agent also believes that other axioms are equivalent to the ones in the theory, and which axioms the agent believes are equivalent may change over time. And so there's a sense in which the agent's beliefs about dynamics do change. To illustrate, suppose an action theory includes this SSA. It says that X will be held after performing action A, just in case either A was the action of picking up X, and AB1 was false, or X was already held. Note that AB1 is an abnormality predicate. Now, under some conditions, the agent will assume AB1 is false, since situations with fewer true abnormalities are more plausible. So the agent then will also believe this other SSA, where we substitute false for AB1. And that can be simplified as shown here. Now, suppose that the agent later revises its belief about AB1 and now thinks that AB1 is actually true. Then the agent will believe this SSA, where we substitute true for AB1. So now the agent believes that what's held cannot be changed by anything. So we've seen how beliefs about dynamics can change. Next, we'll consider how SSAs can be written following patterns so as to make the agent change its beliefs by the desired amount. Remember how one of the generalizations that we wanted the robot to be able to come to was that it can pick up any object other than one which it's failed to pick up. To get that sort of behavior, we can use an SSA like this one, which is similar to what we just saw, except the abnormality now has an additional argument, x. Now intuitively, if the agent comes to believe that a particular object is abnormal, for example, by observing that it failed to pick it up, the agent will come to the general conclusion that all actions will fail to pick up the object. At the start of this presentation, I gave examples of 3 different levels of generalization from an unexpected observation. There may be exceptional objects on which actions always behave differently, as we just saw, exceptional classes of objects, and there may be one-time exceptions. Each of these 3 forms corresponds to a different pattern referring to abnormalities within an SSA. These patterns are described in the paper. Furthermore, multiple abnormalities can be combined in one SSA to support iterated belief changes. For instance, the robot example with the sequence of belief changes that I initially described is formalized in our paper using this SSA. I won't go into too much detail here, but note that we have different disjuncts, abbreviated as the imp-I expression, corresponding to different implausible cases in which picking up an object will fail. We also have associated weights with the abnormalities. Those are the superscripts, which affect how they're counted when measuring plausibility, to control just how implausible the different cases are. And so we've reached the end. We presented an approach to modeling changing belief about domain dynamics in the situation calculus, using action theories that assign plausibility to situations by counting abnormalities. There's a lot more in the paper. We describe the patterns for writing SSAs. We have some more general results about changing beliefs about domain dynamics. And finally, we also describe how to apply regression rewriting with our theories. Regression is a reasoning technique commonly used with the situation calculus. Notably, we describe how to use beliefs about dynamics, and not just the axioms written in the theory, within the regression procedure. Thank you.